I will present the second application entitled Performant DAQ System Interfacing the DSP56303. My colleague Dan Chiciudean will explain the general system architecture and operation.
The general architecture of the proposed system consists of three main components: the DAQ system, the Motorola DSP56303 evaluation module, and the host computer. The DAQ system provides the analog to digital interface logic to the EVM, acquiring the analog input signals, converting them to digital codes, which are further sent to the evaluation module for processing. The core of the DAQ system is the analog to digital converter circuit ADS774 directly connected to a pair of octal buffers. The Motorola DSP56303 evaluation module, the second main component of the system, is connected to the DAQ system through a specialized interface implemented with the on-chip port A signals. The onboard DSP reads in a periodic manner the conversion results from the DAQ system and performs all the necessary digital data processing, which in the digital oscilloscope case are signal synchronization, time-based generation, minimum and maximum value calculation, and the fast Fourier transform calculation. It further communicates with the host computer through a custom design ECP parallel data link to exchange commands and data. The host computer implements the graphical user interface and the interactive control platform of the system. The digital oscilloscope proposed as a case study features a highly interactive graphical user interface implemented on the host computer under the Linux platform. It is composed of a main window to display the acquired signal in real time along with its current parameters such as amplitude or frequency. A second window displays the spectrum of the signal in real time as well, using the fast Fourier transform algorithm on the DSP. The oscilloscope controls window provides the interactive interface for changing its functional parameters like the signal synchronization level and type on the falling or rising edge of the signal, the time-based control, sliding bars for positioning the time cursors on the signal display window, the vertical bars, sliding bars for positioning the amplitude cursors, the horizontal bars, the control button for automatic or manual calculation of the peak-to-peak signal amplitude, and the display freeze option.
As a practical demonstration of the digital oscilloscope operation, I will set an analogic input signal of a rectangular shape and of randomly selected frequency and amplitude using a programmable function generator. Its parameters will be calculated using the oscilloscope graphical user interface on the host computer.
First, we calculate the input signal amplitude using the corresponding horizontal cursors on the signal display window of the oscilloscope interface. The frequency of the signal is further calculated using the vertical time cursors. Another method of frequency calculation featured by the oscilloscope is by using the signal spectrum display window and the corresponding frequency cursor. Modifying the oscilloscope time base results in a better resolution for calculating the signal frequency in the signal spectrum window. The resulting input signal parameters correspond to the ones set with the signal generator.